Okay, for this review problem, we're going to take a look at this autonomous differential equation, y prime equals y cubed minus 4y squared plus 4y. And we're going to sketch sample solutions of this differential equation without actually solving it. The reason we're going to be able to do this is because the right-hand side has no t's or x's in it. It strictly has y's and y's only. And therefore, that makes our job in solving this differential equation somewhat easier. So let's write this as y prime is equal to y times y squared minus 4y plus 4. And that further factors as y minus 2 quantity squared. Okay, now there's a couple of ways of getting at the equilibrium points. The first is using a sign chart. So here are the constituent parts of the right-hand side, y and y minus 2 squared. And when I multiply those together, I get the derivative of y prime. Clearly, the equilibrium points are going to be 0 and 2. Y is 0 at 0. If y is greater than 0, clearly it's positive. And if y is less than 0, clearly it's negative. Y minus 2 quantity squared is 0 at 2. Otherwise, it's positive because I'm squaring something. So multiplying, we get negative 0, positive 0, positive. So if the derivative is negative, that means the solution is decreasing. If the derivative is positive, that means the solution is increasing. And over here, if the solution is positive, that means the solution is increasing as well. So just looking at the arrows, we see that this is an unstable equilibrium, while this one is a semi-stable equilibrium. Okay, that's one way of assessing or characterizing the equilibrium points. The second way of characterizing the equilibrium points is by taking a look at the derivative, and if necessary, the second derivative of this. So let's take f of y is equal to y cubed minus 4y squared plus 4y. Then the derivative is equal to 3y squared minus 8y plus 4. Then I can plug in the equilibrium values, and depending if this is negative or positive, that'll tell us if it's stable or unstable. So if I plug in 0, I get 4. And the number 4 isn't important. What is important is that it's greater than 0. And so that means that y equals 0 is an unstable equilibrium. If I plug in the other equilibrium point 2, plugging in 2, we get 12 minus 16 plus 4. That's actually equal to 0. So from that, I can't figure out quite yet if it's semi-stable or not. What I have to do first is figure out the second derivative. That's going to be 6y minus 8. And if I plug in 2 into the second derivative, I get 12 minus 8, which is 4. And the number is not so important, but the fact that it's not 0. So that means that y equals 2. Because this is equal to 0 and this one's not 0, that is a semi-stable equilibrium. If both of these turn out to be 0, then the test fails and we have to resort to the sign chart. Okay, so we're almost ready to draw pictures. We know where it increases and decreases. But we have one more tool at our disposal, and that is using f prime to be able to figure out the points of inflection. So f prime of y is equal to 3y squared minus 8y plus 4. Now this factors. This factors as y, 3y, minus 2, and then minus 2. So 3y squared plus 4 here, and then we have minus 6 minus 8 here. So that factors. So if I set this equal to 0, that gives me y equals 2, or y is equal to 2/3. Now this one doesn't count because 2 is an equilibrium point, but y equals 2/3 is going to be my point of inflection when I draw the picture. Okay, so with that, let's draw the picture of the curve of the sample solutions. So here's y equals 0. Up here is y equals 2. I'll put a dashed line here. And on this scale, 2/3 is going to be this line here. So anytime I cross this line right here, it's going to change concavity from concave up to concave down, or vice versa, depending on the solution. Okay, so let's start sketching. To the left of 0, the graph is decreasing. So if I'm below 0, the graph is decreasing. So it's got to go something like this, and there's no points of inflection on this side, so it's strictly just going down. Okay, to the right of 2, or above 2, the graphs are increasing. And there's no points of inflection out here. The only point of inflection occurred at 2/3. So the graphs will be increasing upward like this. And they don't cross because every initial value problem has a unique solution. The more interesting case is what happens in between 0 and 2. According to our picture, it's going to increase from 0 and then approach 2. So the graph will increase from 0, and then at 2/3, the graph must change concavity from concave up to concave down. If I started here, concave up, and then changing from concave down. So that's a very subtle thing in the picture to be able to draw. So changing concave up, then to concave down. So that's a very subtle thing to be able to draw in the picture. Then over here, just would simply go like this, because the change in concavity would actually occur over here to the left. So if I were to just extend this out to the left, it would change from here and then go concave up like this, then change here and then concave down over here. Same for this curve here. It would be concave down to that point and then change concavity concave up as I approach 0. And I shouldn't have drawn this so instead. Okay, so those are sample solutions of the curve, which I can draw with reasonable accuracy without actually solving the differential equation.